Hi everyone. Thanks to Infinite Red, and thanks to all the people who sponsored and everyone who put this together. It's really awesome. It's an awesome event. Awesome to be up here. Okay, so today I want to try and add a little bit of context to some buzzwords, and hopefully you can come away knowing a little bit more about how the buzzwords are maybe useful. A quick intro. I'm Eric Baer. I work at Formidable in Seattle, building big JavaScript things. Most recently, I did some fun stuff for Starbucks on their mobile ordering platform. Come ask me about it. Find me on Twitter if you have any questions. Okay, so jumping right in. I'm going to start by just addressing the elephant in the room. New things are exciting. I guess we're all here to talk about new things. That's fun. But somewhere in the back of your mind, you're probably thinking something like, why do we need more tooling? Or like, why do I care about API design trends? REST is like, it's fine, REST-ish. You can kind of hack around some of the problems. And these are really legitimate and reasonable questions. Here's why you should care. So the benefits of any new tool or technology have to be weighed against the cost to bring it into the system. And there's a bunch of ways to measure that. There's the time to learn. There's the time to convert what you have. There's the overhead of maintaining multiple systems during the rollout or the integration process. And with really high costs like that, new tech has to be better or faster by a huge amount. Incremental improvements are exciting, but for most people, they're not worth the investment. I mean, unless you're Greenfield. So the things I want to talk about today, and GraphQL in particular, are in my opinion a huge step forward, and they more than deliver enough benefit to justify the cost. So to understand some of these new tools and what makes them great, I want to talk a little bit about APIs in general and the trade-offs that got us to where we are today. So with that, I want to kind of go back in time. And the first stop is the mid-'60s. And I started looking up a couple of things about the 60s, and I found this amazing thing on Wikipedia, which is like the most useless thing on all of Wikipedia, and it has a citation, which is like even more amazing, and it's still there. So I'll leave that up there, and I'll talk about the 60s. So in the 60s, computers were large enough and expensive enough that API-driven application development that we kind of take for granted was pretty much just theoretical. Because of bandwidth and computation and other performance constraints, most APIs were just mechanisms to run code on another computer. And so from the 60s with ARPANET, all the way up into kind of the mid-'90s with things like Corba and Java's RMI, most computers interacted with each other with using remote procedure calls, which is a client-server interaction model where a client causes a procedure or method or function to execute on a remote server, which is not to be confused with what some people call remote procedure calls now, which are just named methods or named API calls. Anyway. So there were and there still are a lot of really good things going for RPC. The ability to treat a remote environment like it was a local one, albeit slower and less reliable, can create a continuity to otherwise distinct and disparate systems. And so like many things that came out of ARPANET, I think it was ahead of its time. I mean, since then there's been a lot of research into how to embed asynchronous and unreliable interactions like DB access or network requests into the normal flow of a program. Async await is the newest exciting thing. But it's possible that if things like promises or futures or scheduled tasks had been available, the API landscape now would look a little bit different. There are, however, a number of things that make RPC really difficult. So with continuity comes context. And what I mean is that RPC by design creates a little bit of coupling between local and remote systems. You kind of lose the boundary between your local and remote code. And for some domains or some teams, that's okay. But it's not quite as flexible as something that's a little bit more data-oriented. More importantly is the proliferation of API methods. So in theory, a small, thoughtful API surface is exposed that can handle any task, but in practice, capabilities grow, and there end up being a large number of endpoints, because RPC is sort of, by its definition, a bit bespoke. And if that weren't bad enough, it takes a lot of discipline to really prevent APIs from overlapping, maintaining proper names over time as team members come and go. Customer becomes user and that sort of thing. Some of this could be solved with introspection and tooling, but like, I don't know, it's 2017, we still don't have that. So like, I think that's kind of an unfair thing to throw at RPC. So the next major API type to come along was SOAP. It was born in Microsoft Research in the late 90s. It was intended to address some of the practical drawbacks of RPC by adding a bit of structure. So SOAP is just a messaging protocol for exchanging structured information. It was meant to be like a platform, something extensible and a foundation for building complex APIs. SOAP was among the early moves in the direction of resource-oriented APIs. Since using a SOAP endpoint, you could request data of a predetermined structure rather than think about the methods required to generate it. SOAP, it also had some good things going for it, despite its sort of unbearable verbosity. It started a move away from the more procedural APIs and towards a more declarative model when they were workable. Contracts ensured somewhat predictable results. It had the ability to auto-generate some documentation and integrate with IDEs. But the big revelation for SOAP is resource-oriented calls and guaranteed client-server contracts. The biggest downside of SOAP is that it was like impossible to use without lots of tooling. You needed tooling to write tests and tooling to inspect responses and tooling to parse all of the data. And yeah, I mean, it's XML. You could read it. I mean, it's not like a binary thing, but it was a lot of XML, and it was pretty hard to read. It's possible this was just part of Microsoft's strategy in the 90s. SOAP is still used in a lot of older systems, but the hard requirement on tooling makes it kind of too cumbersome for new things, and the number of bytes needed for all of that XML makes it a kind of a poor choice for any mobile network or a distributed system or any of the sort of more chatty things. So the latest design pattern for API development, I'm sure everyone's pretty familiar, is REST, introduced in a doctoral dissertation by Roy Fielding in 2000, and it you know, philosophically, it swung the pendulum in a fully different direction. So REST is really the antithesis of everything that was SOAP. And when you look at them side by side, it sort of feels like Fielding's dissertation was a rage quit. Yeah, I reached out to UC Irvine, Dr. Fielding's alma mater, and they were kind enough to share some footage of Fielding working with a SOAP API just weeks before he met with his thesis advisor to talk about REST. So this is that moment. So SOAP used HTTP as a dumb transport and built structure in the request and the response body. REST, on the other hand, throws all of that out, throws out the client-server contracts and the tooling and the XML and the bespoke headers, and it replaces it with just HTTP semantics. So standard HTTP verbs like, man, that's a mouthful, get, put, post, for fetching and updating data, and URIs that just reference a particular resource in a hierarchy. So REST changes the thinking from modeling interactions and programming with remote services to simply modeling the data of a domain. In other words, REST is fully resource-oriented, and a developer is no longer supposed to know or care what it takes to retrieve a given piece of data, nor are they required to know anything about the implementation of the back-end services. So it's really simple compared to the patterns that came before it. It's easily cacheable, or supposedly. It's simple to scale because it's supposed to be stateless. And since it models data rather than anticipating customers' needs, it dramatically reduces the surface area for APIs. So it's simple to implement, simple to maintain, and simple to scale. But REST, like all silver bullets that came before it, is not without its flaws. And I'm sure a lot of you, as mobile developers, are acutely aware. So to talk concretely about the shortcomings, I'm going to go over a basic example just to use as a reference for the rest of the talk. So let's pretend that we're going to build a landing page of a blog which just displays a list of posts and their author's name. So, and we're going to assume a nice REST API. So first we fetch our list of posts from our post endpoint. Our API will return a list of all the posts and the URI required to fetch additional information about each one. Alternatively, if you work in a real world, maybe your API returns a list of IDs that have to be concatenated with some URI that you have to find on Confluence. Same thing. So next, we fetch data about each of the posts. And finally, we need to fetch the author for each post. So we have the data. It's really well organized. It's very nice. It's easy to read. But it took us 8 calls to get here. So the ergonomics of developing REST clients and servers is certainly better than what came before it, but a lot's changed since Fielding's paper. It was 2 decades ago. I mean, at the time, like the circumstances were different then. At the time, we were in the middle of the explosion of personal computing. Moore's law was a household, like just a phrase that everybody knew, which is kind of surprising. Every year, processors were doubling in speed, and you could get more memory, and networks were getting faster and faster. And then, like 2007, 8, 10-ish, mobile computing came along, and like we regressed a decade. And so that kind of brings us to I guess that forces us to rethink some of the things that we were relying on with REST that made it good at the time. So that brings us to the 3 main weaknesses. So REST is chatty, it returns way too much data, and it lacks any tooling for introspection. So the most important thing I want to point out about REST services is they tend to be very chatty. So what I mean is it takes a lot of back and forth between the client server to get all the data that you need, which can have pretty devastating performance impacts. I actually recently worked on a client where loading a page required almost 40 API calls to stitch everything together. I don't know, I think that's just a reality for a lot of non-greenfield development. So, like skeptics, I can only assume that at least some of you are thinking like, whatever man, we're doing what we can, I'm not Alex Russell, like, besides I was like streaming House of Cards. It's true, we have decent networks, but unlike Ken Wheeler, I'm gonna quantify that claim. And yeah, so to do that, I'm going to take a bit of a detour and look at how mobile devices and HTTP itself works. So the first problem is latency, which is just the amount of time that it takes for a bit of data to move through a network. So that's either you're sending 1 byte or 1 gigabyte. It doesn't really matter. This is constant for any given network type. So for a wired network, we're talking about electrons through copper or maybe light through fiber. For mobile networks, things get considerably more complicated. So unsurprisingly, it's much higher. Latency for today's fastest 4G is still triple that of a wired connection, and 3G is an order of magnitude higher, which still covers most of the world. So the only real important thing to know about latency is that there is overhead for every request, and no amount of technology can overcome that fact. Latency is a hard physical property. So if we think back to our example blog, you take those latency numbers and you imagine a best case scenario. So a new phone, reliable network, 4G connection, you've spent half a second. That's a significant percentage of a reasonable performance budget on pure overhead. This is not you haven't even downloaded data yet. So this doesn't include server response time or the time it takes to render or paint the UI or what have you. Yes, I will acknowledge that HTTP2 has the potential to improve some of this, but unless you're working in Go or all of your things go through, I don't know. H2 works really well for static resources, but I've yet to see very many APIs that serve their data over H2 connections. And what's more, Node is not even possible in Node, and probably won't be for some time because of the TLS termination issue. So I'm going to kind of put that aside. So if that wasn't enough, there's another problem, and it has to do with TCP, which is the underlying protocol for HTTP. So the long and short of the problem is that nearly all connections are made over an asymmetrical network. So the data center or whatever will have a much higher bandwidth connection than a mobile device, and if a server were to send data at 100% of its capacity, the mobile device would immediately be overwhelmed. So to solve this problem, TCP does something called slow start. You don't need to worry too much about the graphs. They're just really to illustrate the shape of what's happening. Slow start just means that the server will send information progressively faster until the client starts failing, dropping packets. The implication of this is often that one big request is much faster than many small ones because it spends more time downloading at full capacity. So the last piece of why this matters, I'm not going to get into too much, but it's how mobile devices and specifically their radios work. So the radio is one of the most battery-intensive parts, probably second to the screen. And so in an effort to improve battery life, the operating system is going to turn it off at every opportunity. So that actually adds overhead. So you have to, whenever you make a request, if your radio is not on, you have to turn it on. So that adds additional overhead to these requests, but it also can drain the battery super quickly. Okay, so the next problem here is that REST services tend to send way too much information than is needed. The API authors, they have to anticipate every use case, and most often you send a complete resource whether or not the client needs it. So in our blog example, we get back all of this stuff, all the posts and all of this data, but actually we need about 17% of that, so that's a 6x loss. In a real-world API, this overhead can be enormous. I've worked on e-commerce sites where the data representing a single product is thousands of lines of JSON. And when you have a product and a carousel of a few recommendations, we're talking many thousands of lines of JSON. Most of that is wasted, 95% or so. So the final thing is that REST APIs lack mechanisms for introspection. I'm not going to dwell on this one either, but without a contract between the client and the server, there's no good way to generate documentation reliably or to create tooling or help developers explore and interact with the data like there was with WSDLs and Waddles with SOAP APIs when they worked. So to be honest, I can count the number of times, probably on one hand, that I've used like really exceptionally well documented REST APIs. Many of them are just poorly documented or not documented at all. So there are, of course, a lot of people trying to solve these problems in a lot of different ways. Some people just write custom endpoints, sort of like an aggregation layer. There is OData and JSON API, both of which are like really thoughtful standards around REST with great teams. They help you get a grip on tooling and APIs. But maybe with an understanding of the things that have worked and not worked in the past, and we can work towards maybe a new foundation instead of just small baby steps forward on something that we already have. So given today's constraints and 2 decades of research into languages and better tools and servers and things, what would we sketch out if we wanted a better API? So we'd probably start with minimal HTTP traffic. We definitely know that there's serious overhead associated with network requests, from battery to latency issues, and so we probably want a way to request what we need in as few round trips as possible. We also know that the average client is resource constrained likely in CPU and memory and bandwidth, among other things, and we probably want to try our best to send only the information that a client needs. To do this, we'll probably need some sort of mechanism for the client to ask for data. So the next thing is that it needs to be human readable. So we did learn from SOAP that an API that isn't easy to use, people will just sort of grimace at over beers. We need to use programs that we're accustomed to, like curl and wget and Chrome developer tools and Charles and whatever else, without having to rely on something bespoke. The reverse of that, though, is that we still want to be able to use tooling. Like, we want to start small and sort of iterate forward. So we did learn from SOAP that client-server contracts are super useful. And in a dream world, we would have sort of the lightness of something like JSON or YAML with the introspection capability of something that was highly structured, like SOAP responses were, and hopefully type-safe. Maybe we can generate our models for native development. And so the last thing is a little bit different. I haven't talked about this yet. It would be really nice if we could preserve local reasoning. So really all I mean is that every project is a little bit different, but over the years we've developed some nice ways to organize our code, and for the most part, all code relating to one feature is contained in one area. We try our best to create some cohesion, except for our data. We have that one giant data layer that's just a blob that's tightly coupled to everything else. So it would be nice if we could encapsulate each component or module's data needs along with its other functionality. Without this, we end up with centralized access, which is just not ideal. Sorry, yeah, I was having fun last night with animations. All right, so what might that look like if we imagine how we might fetch data for our blog example? So on the right, we describe the data that we want in a format that looks kind of like JSON, and in sort of it's nice and readable. Query says we want posts, and from each post we want the title, and we want the author resource, and from that we want the author's name. So if I send that to the server, I might get something like this back. We have a list of posts, and inside each one is the data we requested, which is good. If this were possible, we would fulfill our wish for minimal payloads, since we're converting 8 requests into 1. It also fulfills our need for minimal HTTP traffic, but modularity and local reasoning are not so much. If our blog has an author component and a post component, requesting data all at once like this would break all of the best practices that we talk about, principle of least information, or locality, or encapsulation, or however you want to talk about it. So if we break the query up in a way that could give each component only the data that it needs, we might do something like this, but now we've broken the minimal HTTP thing. And in a real app with dozens or hundreds of data-backed elements, this could be way more chatty than before. So we can fix that if we merge those together, the 2 requests. And that can be actually accomplished really easily with a small tweak, and that is if our query language is a formal language that can be easily parsed and sort of recombined, if we're not relying on some sort of unknown structure. And in fact, if we had a formal language that defined how we write queries, we could do a lot of really interesting things. We don't have to do these things, but we could do things like intercepting all requests and batching them, similar to how the virtual DOM intercepts all DOM manipulations and batches them. We could use a compiler to extract all of the small queries and build at build time and pre-cache stuff. So that we have a lot of good options here. I touched on this on the last slide, but the last item here was tooling. Something that earlier protocols maybe got right was allowing the server to publish a schema that defines its data. By using strongly typed schemas, tools can do things like statically analyze queries. They can optimize data fetching. They can integrate with IDEs. They can do query validation. They can generate models. So this is the part where I tell you that I lied a little bit. These types of APIs in various forms are emerging all over the place. We're at a point in time where we're trying to move past REST. Meteor has been trying this. Rethink, rest in peace, launched Horizon a while back that was trying to do some of these things. A number of graph databases have tools kind of like this. Netflix has Falcor, which does a lot of these things. And of course, the last one is GraphQL, which came out of Facebook, which is actually what I used to model the Dream API. That was actually GraphQL's syntax and semantics, at least in its JavaScript implementation. So I actually really love the simplicity of Falcor, but it's impossible to overlook the developer mindshare and just the dominance of GraphQL right now. So for the rest of the presentation, I'm going to focus on GraphQL, its semantics, and since I really can't imagine anything better than the description on their homepage, I kind of plagiarized it for this slide. It's good. So in GraphQL, you describe your data as a graph of interconnections. Your client asks specifically for the data that it needs, and the GraphQL server returns the result of the same shape. So I'm a little, it's a shorter time slot, so I'm not going to do a demo today, but I encourage you to check out some of the amazing blogs and videos and tutorials out on the web. And actually, what time is it? There's a new tool that's launching, I think, at 11 o'clock today to help teach GraphQL. Anyway, check out Twitter. I'm sure it'll be all over the place, but check it out. Before I go, though, I do want to mention a few of GraphQL's more interesting properties that you should be thinking about should you decide to pursue it further. So first, GraphQL is a spec, and it's only a spec. It is not an implementation. The JavaScript implementation is one of many. The spec defines a type system, and it defines a query language, and it defines a couple of validation rules to ensure that a query can be run against a schema, and that's all. So all of the associated ecosystem tooling, all of the Apollo stuff and the Relay stuff, it's really neat, but those are things that are possible on top of GraphQL, but those are not GraphQL. So just keep that in mind. So there are implementations in over 24 languages, which means, and JavaScript's one of them, so it's sort of bring your own backend. GraphQL is also agnostic to its data source. So, if in the same GraphQL server, you could fetch data from Redis and like the USPS address lookup API and internal APIs, and the client would never know the difference. It's all sort of about aggregation. And after working with GraphQL for a while, I've begun to realize this is kind of how we've been building software for years. I mean, there's almost always, whether it's in the client or the server, almost always there's a layer, and you can call it a translation layer or an orchestration layer or a transformation layer or a DAO layer, whatever you want. It ingests data, and sometimes from multiple sources. It reformats it and then passes it on to a presentation layer. So GraphQL is really just a generalization of what we've been doing already in a platform-agnostic abstraction. So the next thing is that GraphQL is really good about progressive disclosure of complexity. So GraphQL does a fantastic job of making simple things simple and hard things possible. This slide is a really good example, actually, and the blog thing. To get immediate use and feedback, it's really straightforward. The demo that I have goes from 0 to GraphQL server deployed on now in about 7 minutes. You can layer GraphQL onto an existing REST API. I actually think that's a really great use of GraphQL. And that lets the clients get, you can even let clients just use regular HTTP GET, like just fetch, like however you want to do that. You don't need to use the fancy tools and integrations, though you can. If, though, you want to go all in on GraphQL and you want to build, build on that foundation and do like field level authentication and mapping complex data and do subscriptions and like there's so many cool things that you can do, but you don't have to. So you can start small and build up to the complexity of your system. So the last and most important is that GraphQL is a server that publishes what's possible and lets clients decide how to use it. So this stands in really stark opposition to publishing a pile of resources and saying, hey, run joins over this. So it really allows for a lot of nice tooling. Like the developer experience of using GraphQL is really wonderful. And in fact, I've been able to pull in a lot of the PMs and QA teams that I've worked with because they're able to explore and manipulate the data themselves in a really intuitive way. Check out the tools; they're just so cool. Wish I could show you. Okay, so before I close out, I do want to say that I love GraphQL. Find me on Twitter, message me, email me, whatever. I'd love to talk about it. I'd love to hear like how it's working or not working for you. I believe the hype is justified, but also there's no silver bullet, and I don't want to pretend that there is, and I don't want anyone walking away thinking that this is like the magic solution to all the world's problems. So GraphQL is great, but it's not without its flaws. A couple of them. So GraphQL seems like a tool almost purpose-built for good data. Facebook may have immaculate APIs. I don't. I have to work with things that are maybe a little messier, require a little bit of polish. And I found that complex manipulation of data, it's easy to just traverse a graph if your REST API has hyperlinks already. But if you have to manipulate the data, that can be a little hard to manage. When part of a query fails, because you can have multiple queries and you can request data at an arbitrary depth, when part of that fails, GraphQL, at least by default, will return a partial result. This is great. You can turn this off, by the way. This is customizable, but this is their default behavior. I think it was a correct choice, but it definitely makes I think it makes error handling a little bit more complicated, maybe more robust, maybe better, but your clients have to think about whether or not data will be missing from the tree. That's if you choose to use that feature. Analytics and monitoring are still catching up. Organizing a large schema and preventing drift over time is difficult enough that there are conference talks about it. Running large queries can peg your CPU. There are strategies to mitigate this, but GraphQL can be resource intensive. So anyway, all of this is solvable. It's not that bad. I think GraphQL is sort of, it's the only technology I've gotten a chance to work with that really lives up to its promise. But I did pick on everyone else, so it's only fair to have a slide like this. All right, so I spent most of this talk presenting about like why GraphQL exists and the problems that it solves, and less talking about GraphQL semantics and how to use it, how to get started. If it piqued your interest, please go out, learn in whatever way makes the most sense for you. Go check out YouTube, or I mean, even the spec is pretty. It's actually very easy to read. This is about all I have time to share. I hope at least a few of you will go out and explore, check out GraphQL. Here are some links. Definitely check out the Learn GraphQL, check out the spec. Find me on Twitter. Thanks, everyone.